Hi everyone, welcome back to day 8 of Qiskit Global Summer School. And in the next 2 days, we are very exciting to dive into the future of quantum computing with the fault-tolerant quantum computing that IBM is planning to build towards by the end of the decade. And to kickstart it, we are really honored to have Professor Barbara Tehau, who's a pioneer in the field of quantum error corrections, and to give us a historical development of quantum error corrections. And Professor Tao is actually one of the first, as I understand, to get PhD in quantum computing in the Netherlands. And after her PhD, she moved to IBM Research as a postdoc and then later as a research staff member. And after IBM, she went to RWTH Aachen University and later moved on to TU Delft. So, Professor Tao, we're happy to have you here.
Right. Well, thanks for having me and inviting me to give a talk about the history of quantum error correction. I will be focused on the early history of quantum error correction. I'll say a few things maybe about later years, and maybe this will also come up in the Q&A. The reason maybe for me to emphasize the very early history of quantum error correction is that basically the theoretical part of this history occurred very quickly in the years 95 to 97. I myself was a starting PhD student in 95, so I kind of experienced some of it, although I wasn't maybe fully aware of the importance of it at the time, being a young PhD student. But I'd like to go over with you about some of the developments that took place in those years, and kind of explain what are the important innovations there, who played a role in this, and what came out. Of course, there will be lectures by John Watrous after me, and they will definitely go in much more detail about the technical aspects of error correction, stabilizer codes, and so on. So the thing is that I will be maybe a little bit short here and there and mention something, and you say, well, what is it really? And then I would recommend you, you listen to John Watrous lectures, while he's giving them live or later when you have time to do so. I'd like to start with actually a quote by Andrew Steen. So a few people played a big role in this very early development, and one of them was Andrew Steen, a professor at Oxford currently. And he wrote 2 papers on quantum error correction. And this is a quote from his second paper. And maybe we can understand the sort of scene in the year 94. In 94, Peter Shor came up with the factoring algorithm, how you factor a large number into its prime factors on a quantum computer, which was a major breakthrough and a reason to want to build this quantum computer. But of course, immediately physicists and computer scientists and mathematicians started worrying, what would it take to build this device? And I think Andrew Steen had a very interesting perspective on this, because he asked, is decoherence fundamental? And this is a question that other physicists have also asked themselves, like Schrödinger, for example, much earlier. So let me just read out what he wrote in this paper. However, it can be argued that the possibility of decoherence is itself just as fundamental a feature of quantum mechanics as the interference and entanglement of which a quantum computer takes advantage. Such decoherence must be considered, for example, in any discussion of the Schrödinger's cat paradox. The cat in Schrödinger's short thought experiment, it corresponds here to the quantum computer itself. Let me pause for a moment. So we believe the Schrödinger cat, you've probably heard about it. The cat can be dead or alive, and then quantum mechanics says it can be a superposition of dead and alive. But really, we will never observe, or it's unlikely that the cat will actually remain in the superposition of dead and alive, because the cat is a very macroscopic object. It's made out of many degrees of freedom, its hairs, its brains, its whatever. And, we have very little control over these degrees of freedom. So he says that the quantum computer is sort of like the Schrödinger cat's, experiment to its extreme, in the sense that we need to create very macroscopic quantum information, carried by many degrees of freedom. And the question is, can we do this? Can we beat decoherence? Or is this computer fundamentally a flawed idea because decoherence always inevitably take over. So then he says, hence the idealization in which decoherence is taken to be negligible is not merely a limit on the practical application of the theory of quantum computation. It's in fact an idealization too far, since it involves neglecting a basic aspect of quantum theory, as has been emphasized by Landauer in 1995. Ralph Landauer was also a physicist at IBM, who was at IBM still when I was also there as a visitor, and he was quite critical of the idea of building a quantum computer at the time. So why I find this quote very interesting is because we can be critical of whether we could build a quantum computer in the year 95. But instead of just being critical or saying, oh, physics is this way or that way, and that's just the way physics is. No, instead, people like Shor and Steen came up with very explicit mathematical schemes how to actually get rid of decoherence. Because I believe the theory of error correction and fault tolerance is basically that. It's basically showing that we can make macroscopic quantum information. We can make a cat being a superposition of dead and alive as long as we control all degrees of freedom very precisely and we can correct errors. So this framework that was sort of put together in these 3 years and with many results later was very mathematical. It took mathematicians. Well, Steen was actually not a mathematician, but Peter Shor was. Kitaev was also fairly mathematically oriented, as I'll show you in a moment. But it took maybe mathematicians to be creative and saying, hey, decoherence is not fundamental. We can have error correction codes. So the first error correction codes were by Shor and Steen in 95 and 96. And so this paper of Steen, of which I quoted some text, was 96. So the first paper really that showed that you could have a quantum error correction code was a paper by Shor, and this was received in May 95. So this was a breakthrough in terms of a few new essential key insights. And I know John Watrous is going to talk more about how this code actually works, so I'm not going to cover this. But I do want to stress what are the key insights. And again, I'm going to cite Shor. And because this is one of the key insights, he writes, to preserve the state of superposition of the encoded qubit, what we do in effect is to measure the decoherence without measuring the state of the qubits. This is a crucial insight, because usually the issue is that, say, maybe, we would like to learn about errors, but we don't want to measure all the qubits so that our quantum information is lost. So can we separate the two? So in his code, what you have is that you have 9 physical qubits, and you encode 1 logical qubit. That's what also called is the encoded qubit. This code can correct any single qubit error. These details are for now not important, but what we can do is by careful measuring involving ancillary systems, we can determine which one out of sort of 9 errors happened, which qubit was affected. And there's also superpositions of errors allowed, and an error can be written as a linear combination of Pauli matrices, but these things you may see also in Watrous' presentation. Okay, so but what are the new key insights? As I already mentioned, or what the quote already says, is we can learn about which error occurred without learning what the logical state is. This is crucial for quantum information. Classically, if I have a state with an error, I can just sort of measure every aspect of the state without disturbing the state, right? Measurement doesn't introduce any extra disturbance. However, in quantum mechanics, measuring is an act that can destroy or disturb a state. It projects a state in a certain set of discrete states and so on. And what we want to do is we want to measure nothing about the logical state, but we do want to measure information about what error has happened. And to be able to do that is very specific and can be done. And as Shor showed, how to do it basically. His construction and constructions that came later generalized classical codes. So that's also important because there's a huge body of knowledge on classical error correction. And the class of codes introduced by Kelderbank, Shor, and Steen they use classical codes to build quantum error correction codes. So in this first construction, it's not quite of this kind, but at least the Shor's construction. Let me take a sip of water for a moment. Shor's construction generalizes classical codes. It does that by adding redundancy, but it's not by copying quantum information. That's to say, if you have an unknown quantum state, you cannot clone it, you cannot copy it. So he needs a new idea. To be a little careful with my throat, I'm sorry. He needs a new idea, which is to create a highly entangled state. For example, this 9-qubit state involves, this encoded qubit is a highly entangled state of 9 qubits. Another key insight is here that you may think that in quantum mechanics, you have a continuum of errors. For classical error correction, you just have bit flips. But he also showed, and this is being corroborated by later results, that in principle, if you can correct bit flip and so-called phase flip errors, you can correct any errors. So the set of errors you have to correct quantum mechanically is not a continuum. It's discrete, like it is for classical codes, but it is sort of double. You need to correct two errors, two types of errors, X and Z, instead of just bit flips X. All right, let me go back to Steen. So as I mentioned, I quoted a paper in 96, but he wrote an earlier paper. And this was again related to this question of a Schrödinger cat state. So this paper was received in 95, so a few months after Shor's result. And in this paper, he introduced the 7-qubit code. The 7-qubit code is a favorite code now in experiments. It has been realized, and it's a small sort of a baby code or small code in a whole large family of code, and these are the color codes were introduced by Bombin and Martin Delgado much, much later. This is a representation of the code. If you don't understand these things, these are parity checks. As I said, John Waters is going to explain it, but these are the 7 physical qubits, and together these 7 physical qubits constitute our logical qubit, meaning that 2 special states from these 7 physical qubits, namely the state which I call 0 here and the state which I call 1 here, represent my logical 0 and 1. Okay, so what Steen thought about is he asked the following, or he argued that this paper showed the following. Namely, I quote again, "It is shown that a pair of states which are in some sense macroscopically different can form a superposition in which the interference phase between the two parts is measurable. This provides a highly stabilized Schrödinger cat state." So let me sort of unpack this a little bit. So the state 0, which you can kind of see as like an alive cat, and the state 1, which is like a dead cat, are macroscopically different, meaning they are different. If I look at what the values of these bits are, and I compare, they're not one thing for the state 0. They can be all zeros, or there can be a bunch of ones. So there's this is a superposition of a bunch of states, but 1 is definitely all the bits are different. They will always differ in at least 3 places. I'm not showing this on the slide, but this is the case, and 3 here is the macroscopic number. But generally you say, well, you have a state 0 and you have a state 1, and in order to go from 0 to 1, I always have to flip many, many bits, a macroscopic number of bits. Now I can ask about the state 0 plus 1 and the state 0 minus 1. And you can ask, how do I go from the state 0 plus 1, which is the superposition of a alive and a dead cat with a plus, to the superposition of an alive and a dead cat with a minus? How do I go from that? Is that also macroscopically different? And he argues that it is, and it is not always the case. It's just the case for his 7-qubit code. And so this says that this error correction code provides a beautiful example of a cat which is in the superposition of dead and alive and may be stable that way. It's a macroscopic, and it is a highly stabilized Schrödinger cat state. All right, so that's sort of the the background on the first two codes. Now I want to move one step further because I said this is theory of quantum error correction and fault tolerance. Okay, so what's fault tolerance? I want to briefly introduce that concept, and I want to use classical error correction as an example. So classical error correction, there are bit flips. So there's a very simple code, which is called the 3-bit repetition code. Instead of having a single bit, which can be 0 or 1, if we have a 0, we replace it by 3 zeros. If we have a 1, we replace it by 3 ones. Why is that advantageous? Well, if one of the 3 bits flip, then the majority will still have the right value. So if we just compute the majority, then we'll know it was a 0 or we know it was a 1. Of course, this assumes that only one bit flips, right? And let's say these bits flip independently with some probability p. So the probability that one bit flips is order p, and the probability that 2 bits flip is order p squared. Now, if 2 bits flip and we take this majority, of course, we make the wrong inference, right? We had, say, 3 zeros, 2 bits flipped. Now we take the majority is 1. Now we say we stored a 1. Okay, we make an error, right? So this code can correct a single error. If one of the bits flip, we can correct it. So this is sort of depicted like that in the sense that the straight line, this is the probability for error p, and this is the probability that we make a wrong inference. And if, we just use a single bit, then of course the probability that we make an error is just p, that's the straight line. If we use this little code, then we say, well, the probability that we make an error requires there to be 2 flips, right? Because then our majority function was wrong, and that's this blue curve. All right, so that's a very simple principle. There's one more thing that we can say about the repetition code that will be relevant, which is how do we compute with these bits? Well, let's say these bits, or this single bit, was participating in some computation. And it's kind of clear that if I now, every bit in this computation, I take 3 copies of it, and I just do the computation 3 times, and I take the majority of the answer, that's the way to fault tolerantly execute the computation. Right? So the computation on these logical bits is easy. I execute the computation 3 times in parallel, take a majority vote. This will be relevant when we talk about quantum information because it's a little less trivial. Okay, so now I can ask 2 questions about this simple scheme of the repetition code. First of all, I can say, what? You said I have to take the majority vote, right? So I have to look at all the bits. Are they 0 or 1, each one individually? And I just look at what's the majority. And let's say every little computation I do is noisy, is inaccurate. And this is what we're facing with quantum information. Every little measurement operation we do, there will be noise on it. It will have some error rate. So if we take this majority vote, but it's actually it's a bad unit, then we're not helped at all, right? We maybe make things worse actually by doing this. And von Neumann, for this we have to go back to 1956, John von Neumann, the mathematician, he thought about this question about fault tolerance for classical information. He wrote a paper, Probabilistic Logics and the Synthesis of Reliable Organisms from Unreliable Components. It's funny to hear the term organisms, perhaps, because that sounds like it's something related to biology. And I think he actually was thinking about, how do we get reliable organisms, how we get reliable, functioning, living human beings or animals or plants from certainly components that sometimes do wrong things. So we need some, error correction. And he had in his paper, he has a little figure, which looks a little obscure, but it's very simple. So he has a computation with 4 inputs. There are these lines. And what you do, and so this computation has 4 inputs. Here, there are these 4 inputs and has 2 outputs. So 2 bits out, 4 in. Okay, fine. Now we use a repetition code. So we just execute this computation in parallel 3 times. So there are 4 input lines. Each of the inputs get copied to 3 of these organisms, O1, O2, and O3. They each have 2 outputs. And each output gets sent to this majority, right? The first output bit on all the three, O1, O2, O3, gets sent to this M function, and M is this majority function, and the second output for O1, O2, and O3 gets sent to the other majority function. The majority function is computed of these three inputs, and one bit goes out. So by doing that, we have a new unit. And that new unit takes 4 inputs and 2 outputs again. And now the essential question is, will this new unit have a better performance than in the old unit, which is this O1 individually? Why would it have better performance? Well, we take the majority function, and if the majority function maybe has a slight error, then still, most cases, we compute it right, and we can correct single errors in this process. Right? So you can imagine, and this is an intuitive argument, that there's some kind of error threshold. If the error on these organisms, O1, O2, and 3, and M, is small enough, then this new whole unit works better than the old unit, the old, say, O, right? And so if we do this once, that's to say we use this circuit instead of one of these single circuits, we could do it again. We could say, oh, whenever I do O1, I replace it by this new unit which splits it in 3 and then takes the majority and, does this whole thing. And that will be more reliable. So what we say, technically we say we concatenate or we recursively apply this construction. And this construction works if the error rate on O1, O2, and O3 and M are sufficiently low, so that such a new unit works better. If you do this recursively, so every time, you can do it many, many, many times, you'll get more overhead, right? Because every time you split, one bit into 3, and then every one of those into 3, so you get 9 bits, etc. So you get some overhead, but in the end, you get a more reliable computation. So that's an idea that is essentially also used in quantum error correction. So if you get that idea, then that's good, because then you understand the quantum threshold theorem, so to say, that I'll allude to later. The second question we can ask, could we use the repetition code for quantum information? So in quantum information, we don't just use, 0 and 1, which means in this case 3 zeros or 3 ones. No, we want to have superpositions of 0 and 1. So how do we then take this majority vote? Should we be measuring every qubit of these 3 qubits? But that's a problem. If I measure every qubit, say I do this for this state, I'll just be measuring those qubits, say, as 0, 0, 0 or 1, 1, 1. And all information about alpha and beta is lost. So this is this crucial thing that Shor also used. We should be measuring about the errors, but not about the logical state of the qubit. So what we could do is some other scheme of measurement. We could ask, for example, of these 3 qubits, or these 3 bits, we can ask, are the first 2 bits the same or not? But don't tell me what they are. So I have a measurement which says, are they the same or not? The same would mean that they are 0, 0 or 1, 1. And if they're not the same, they could be 0, 1 or 1, 0. But don't tell me that it's 0, 0 or 1, 1. Just tell me whether they're the same. That kind of measurement you can actually set up and is set up in these quantum error correction circuits. There could be a second measurement which says, are the last 2 bits of this 3-bit code word, are they the same or not? So the same idea, just applied to qubit 2 and 3 instead of 1 and 2. So I do 2 measurements. Each measurement gives me 1 bit of information. So that's 2 bits of information. And with those 2 bits of information, if you think about it, you can kind of figure out whether there was no error, or for both measurements the outcome is the same, or whether there's an error on qubit number 1, where for the first measurement, M1, the output is no, they're different, and for the second measurement, the output is yes, they're the same, and also an error on qubit 2, an error on qubit 3. You can determine this. This type of measurement is a parity check measurement, and it's determining the eigenvalue of a product of z's. But for that, don't want to go into too much detail. All right, so I give you a little bit of an idea already what's been introduced by Steen and Shor, the first code called Helderbank-Shor-Steen codes. There's one more crucial idea which was introduced by Kitaev. This is already a little later in 96. And Kitaev used this to show that you could build a fault-tolerant quantum memory. So you could store information. And fault-tolerant quantum memory meant that you could store information for an arbitrary long time, using concatenation, in fact. And arbitrary long time means that you reduce the error rate on your stored quantum information to arbitrarily small numbers at the cost of an overhead. We'll discuss these overhead a little later. Okay, so what's the new idea they introduced? Well, it's sort of two things. One is the idea of a local check code. So we said all operations in our quantum computer are faulty. And we also said, well, in order to determine majority or determine whether, those two bits are the same or different, we have to do little computations that are also faulty. And these are dangerous. And these are dangerous in two ways. And this is, again, a quote from a Kitaev paper in 96. Let me read it out loud. The most dangerous is the first step, the measurement. The measurement, he means, this is the measurement that measures whether an error has taken place, which uses an ancillary system. First of all, a single error in the syndrome can make it impossible to determine the error in the qubits. This is kind of the idea, like, I compute the majority function, but I'm really bad at computation, so I output something that's wrong. Of course, then I don't learn anything about errors. What's even worse, one error during the measurement can spoil all the qubits involved in this measurement. And this is a special thing that happens in quantum mechanics, that while I'm computing this majority function or measuring a parity check, learning something about error, I may actually feed back errors on the qubits themselves that should be protected. So I want to feed back as little error as possible. And this is why he says local check code are especially useful for fault-tolerant quantum error correction. For a local check code, all the measurements can be organized in a circuit of bounded depth. And this is maybe a bit technical, but his code, which is known as the Tor code, which you may have heard about. So for his code, what you have to do is you have to look at groups of 4 qubits, and you have to measure something about their parity. Like, you have to ask them, are there an even number of ones among you in your state? Don't tell me your state, but just, are there an even number of ones? And you do that using an ancillary system. But the important thing about the Tor code, or one important aspect, is that this number remains 4, while the total number of qubits of your Tor code, which is the size of this lattice, can grow very large. So that's what he means by bounded depths. To compute the parity here is a very small circuit. And because it's a very small circuit, there won't be too many errors affecting it. And if there are errors, it will only affect at most those 4 qubits that participate in the circuit. At least this is what we hope to when we realize this. And this is advantageous. So the code size will grow, meaning this lattice will grow. What we do with this lattice, so the qubits of the code are these round dots. There are periodic boundaries here, matching this and that, and matching that and that. So we actually wrap the surface of qubits up into a torus. That's why it's called the Tor code. And so this lattice can grow, but this will stay small. So the errors that I produce by running my parity check measurements are not so bad. And this is very important, and it made sure that the Tor code basically became one of the favorite codes. And later a surface version of this code was introduced, where I don't have periodic boundaries, but I just have a sheet that ends at the sides. Now, one more thing about this local check code, and this also has helped its sort of interest in the experimental community, is that in order to measure the parity checks, I need just to have some extra qubits that are placed on this 2D lattice. So, for example, for these blue guys, I place an extra qubit here in the middle. If you see my cursor, And for the X, for this check, which is slightly different, I'm not going into that, I place an extra qubit. So these ancilla qubits, here's a circuit how to measure this. Again, John Waters will cover this in more detail. They can be placed locally on the 2D lattice. And that is advantageous if I want to work with a chip. Now, of course, IBM makes superconducting chips. Google does that too. IBM even has plans to go beyond 2D because there are codes that are actually more interesting than the Tor code in terms of total overhead, for which you need to have some connectivity beyond 2D. But as a basic code, this surface code, which you can engineer on a 2D lattice, is very appealing. All right. Now, we still sort of in history land. I said something about a local check code, and actually these local check codes that Kitea first introduced have been studied also later in the field under the name of LDPC codes, low density parity check codes. Classically, low density parity checks are the most attractive and widely used codes that there are. And so it was very interesting. It was a very interesting development that we could develop these quantumly. And that actually took quite a while. Only the last 5 years, we know how to have good quantum LDPC codes. And these all have this property is that the checks are local. They're not necessarily local on the 2D lattice, but they affect only very few qubits, not scaling with the total size of the code. All right, we need one more idea. I mentioned that Kitaev had shown in 96 something about fault-tolerant quantum memory. If you have a repetition code, it's easy how you do computation. But how do you do computation with encoded quantum information? That's not so easy. So this concept of how you do it for repetition code, you just do it in parallel on, the 3 bits that you've used, we call transversal. So here's an example. Let's say I replace every qubit or a bit by 3 bits, and I have to do a C0 between the qubit that's encoded here and the qubit that's encoded there. That's my C0 gate. And maybe if it's transversal, I can do it via a circuit like this. I just do these gates in parallel, which is very nice because it's fast. These gates can be done at the same time. And they don't spread errors around because they just act independently between the different qubits in each sort of block. But not all gates can be done transversely. Now, there are ways of doing gates differently, but these may be bad in terms of they spread error around in the block. And before I know it, there's this error spread and a code that can correct many errors. I'm making life worse. It's worse than sort of, having no error correction. So it took a very non-trivial construction and first showed by Shor in 96, to show how you do sort of universal logical computation. So for this, he showed a way how to do the logical Toffoli gate. That's this gate here. And that was highly non-trivial. All right. So then, after Shor's results in Fox 96, the time was ready for sort of putting it all together. And this came all together in what's called the fault-tolerant threshold theorem. It's a crowning achievement. And the names that are attributed to this achievement is Knil, Laflamme, and Zurek, and independently Aharonov and Ben-Or, and also Kitaev. And this theorem was proved using code concatenation, which is this idea that I alluded to that von Neumann had introduced originally for classical error correction. Now, here's a caveat. Don't try proving this on a spare afternoon. What I mean is that this is a highly non-trivial theorem, and there has also been later papers, for example, in 2005, in which they kind of make this theorem more rigorous and precise, because to put all, to dot all the I's is highly non-trivial. But it used, the point is there are some independent influences, but it used, how you do universal computation, what error correction you need, and that you need code concatenation. And the upshot of this theorem is basically the following. So if, let's say I have noisy hardware, but I want to run a circuit of size n. What's the size? It's the total number of single qubit and 2 qubit and measurement things that I want to do. Okay? But I don't have perfect hardware, I have noisy hardware. Now, let's say my noise is sufficiently weak, So the hardware is pretty good and it's local, and that's a technical condition, but just assume that it's fine. This is usually the case. It means that, you know, the probability for many errors is much, much lower, is exponentially lower than the probability for few errors. Okay, so the theorem basically says that this noisy hardware I need is not that much larger than the original hardware. Basically, I need a circuit of size n times a polynomial of log n. And the important point is this is not like 2 to the n, which would be terrible, right? If I had needed an exponential blow up of resources in order to simulate a perfect circuit by a noisy circuit, right? Of course, we care about this overhead, and there's been even further strengthening of it. All right, what do we use in such a circuit? Because of course, at some point, error correction has gone from theory to experiments. And when you do experiments, there's a lot of other things you face. For example, you need to do frequent mid-circuit measurement, meaning you need to introduce ancillary systems that are used to measure out error information, like these parity checks. And this is essential removal of entropy. Right? We need to remove entropy out of the computation. We need fast classical processing of this error information. If we have these bits with information about parity checks, that doesn't mean that we know immediately what errors have happened. We need to run some classical algorithms to process this. And also that some errors that are due to leakage or loss, an atom gets lost and we can code it in an atom, that they actually can be reduced to qubit errors. I'm not going to go into this. So for the surface code, it was shown that you need this threshold, this sufficiently weak, is like 0.75% per elementary operation. And in 2024, there was a big result by the Google team. They were the first team to show convincingly that their hardware was below the surface code threshold, and they could scale up. They could go from a smaller surface code to a larger surface code and get better performance. So this was very a beautiful result. Okay, so I have to see how am I doing my time. I'm now sort of wrapping up. Okay, I'm doing fine. I want to jump over 28 years of history a little bit. As I said, intense efforts took place in the first sort of 3 years. It doesn't mean that nothing happened afterwards, but the pace of developments was slower. So I just want to highlight a few things. In 2001, there was a beautiful paper by Dennis, Kitaev, Landau, and Preskill, in which they said, let's focus on the Tor code and study what the threshold is, study how we classically process error information to determine what the errors are. So what decoding algorithm do we need to use? This is also very important, because this algorithm needs to run very fast. It needs to run at the speed which is at least as fast as the data that we're getting in from these measurements. So this is a beautiful paper that really put the Tor code on the table as a very interesting architecture. One aspect of the Tor code is, say, maybe you have a 2D chip only, but how do you do a controlled knot on this logical level? It can be done transversely, but there are ways to do it by not losing any 2D connectivity. This was Rauschendorf, Harrington, and Goyal, and this was again generalized by Horstman et al. In 2012 to present a technique that's known now as lattice surgery, which is kind of a technical term and which being used and generalized for many these LDPC codes that I referred to earlier. So Shor had this method of showing how to do a Toffoli gate fault tolerantly, and Bravyi and Kitaev introduced, Sergei Bravyi is an IBM researcher, used a beautiful method to get indeed gates like the Toffoli gate to introduce them fault tolerantly into a computation, and that's been a favorite method. So far, many overhead studies use this method to assess how many resources you need for a future quantum computer. As I already mentioned, Bombal and Delgado introduced color codes. We're talking about how these theory schemes have moved from theory to experiment, I believe that Austin Fowler, who wrote a very influential paper with Marc-Antoni Martinez in Cleveland, played an important role, because they said, here's what you have to do if you want to run the surface code. And then experiment to say, hey, here's what we could actually try to do. I also want to allude briefly to these pictures. You may have heard David DiVincenzo give a talk last week. He's my husband. I'm a bit biased. He wrote a paper in 2009 in which he discussed fault-tolerant architectures for superconducting qubits. And these are figures out of his paper, which showed like how you would have, connect couplers and qubits to have a lattice of 2D qubits that could represent the surface code. But I'm certainly dropping out many names here, because the beauty of this field of quantum error correction fault tolerance is that it's a very nice field. People are very friendly and collaborative, and many people have contributed so far and will contribute in the future, I'm sure. I want to make sort of one little anecdotal comment. So as I mentioned, I got my PhD in 99. I started in 95. And I went to Torino in Italy for my first workshop. This was at a place called the ISI, Institute for Scientific Interchange. There was already a workshop in 94, but in 95, it was this group of people. Here is this is me, this is Dorit Anaronov, who's worked on the fault tolerance threshold theorem. Here's Peter Shor, for example. And I just want to mention something. So at this workshop, there were not that many people, but quite a few people were thinking about quantum error correction. Well, Shor's paper was May 95, so people were, it was a very active development. So it being the first workshop as a PhD student, I felt like, wow, it's overwhelming, interesting, but maybe I should think about something else, follow my own trajectory. So actually, that first year of my PhD, I started thinking about Ising spin glasses, very different thing. So maybe you heard that Ising spin glasses have a hard time, finding their ground state. And that's actually a hard computational problem. And then I thought, oh, maybe you can use a transverse field. And that's now called quantum annealing. I didn't think it would solve that hard problem, and I didn't write anything about it. So I'm not sure that was so successful. But I'm mentioning this because right now I am, when I was announced, I am very actively working on quantum error correction. I'm seen as one of the experts in the field. And now there are way more people working on it. So my thoughts, there's already too many people working on this, you see the small group, is definitely true now. Now there are way more people working on it. And here I'm showing just some data from the archive. For example, here on the left, what you see is this is the occurrence of the word quantum error correction versus the word NISQ, which is coined by John Preskill, noisy intermediate scale quantum computing, to denote this area pre-quantum error correction. So here's the number of papers, and error correction definitely has taken, has grown quite a lot in the last few years, more than NISQ. But you have to see this in perspective, of course, because if you look at the word quantum error correction versus the word qubit, you see that qubit is still, is up to 4,000, and quantum error correction is up to 800. Although that's still, a sizable piece of the field. And it has really exploded in terms of activity. And that is because, basically because of the experimental progress and also new theoretic ideas. But the existence of the experimental progress and the platforms, makes for new interesting challenges to solve theoretically, building on, what we already know since 95. All right, let me just look at the time. I have a few comments before I finish. Yeah, I haven't talked much about these experimental realizations. I mean, the idea is I give a historical talk. So there are 3 platforms that are doing very well. One is the superconducting qubits, which is, for example, what Google's done, what IBM is doing with 100 to 1,000 qubits. Then there are the trapped ion qubits, which have the chips that are in use now have all-to-all connectivity. It's not clear that And they have also like 50 qubits, very, very high quality. So you can do nice quantum error correction experiments there. This all-to-all connectivity means that you can do a gate between any pair of qubits. It's maybe hard to scale that in the future. And then lastly, there are the neutral atom qubits that have made amazing advances, doing gates on multiple steam codes and things like that. And they also foresee they could be working with 10,000 physical qubits in the near future. So, okay, so there's many open questions. Is there sort of one best code that we're going to use? And this space is, I think, very open. I just want to make a few comments. So the right code architecture is an open question because it depends on qubit platform. It depends on whether you can move qubits around, whether you have long-range couplers. One thing is you can say we certainly will use modular architectures. That is sort of a given in any, maybe use it because at some point, we can't reliably get a high yield for the chips we make, or there are other issues that start playing a role, but related to laser powers. If we're talking about neutral atoms, so we have to switch to optical interconnects. So modular architectures beyond 1,000 or 10,000 qubits are definitely going to play a role, and they play a role because maybe they'll be noisier or slower. And so any code architecture, which is how you use error correction in producing reliable qubits, will use these facts. But of course, if they're not all known, we can't use these facts. Yeah, and one thing about clock speed of logical processors is also variable between trapped ion qubits, neutral atoms, or superconducting qubits. But the speed of single qubit and 2 qubit gates is quite different for these platforms, in particular superconducting qubits, which are very fast, and neutral atom qubits, which are relatively slow, if you also take into account moving of atoms that they do to do gates. But the clock speed of the logical quantum processor is set by the duration of the quantum error correction cycle, how quickly you measure the parity checks, but also by the type of the way you do logical gates. So there are various trade-offs that play a role. The future is bright, but also open and interesting. So my guess would be we need about 1 million physical qubits, or 10 to the 4, 2 million physical qubits for a quantum advantage, maybe leading to 100 to 1,000 logical qubits. And interestingly, also going back to factoring large numbers, there's been recent progress also using error correction ideas to say, hey, if I want to have RSA 2048 as a result by Gidney of Google, that it used to cost 20 million physical qubits with his estimates with the best method, and now that's been reduced by him to 1 million physical qubits. So that's quite fascinating. Okay, that's the end of my presentation. In big letters, it has moved. Quantum error correction moves from theory to experiment. It will become the digital foundation of quantum information processing. Thank you for your attention, and I'm happy to take some questions.
Hi, thank you for insightful lectures, for following all the historical developments. And let me see. I think.
Shall I stop the?
Yeah.
Stop the steering.
And you can also go to the browser, and you should be able to see the questions. We don't have that many questions at the moment, so please put your questions in the Q&A panel, and we can get started with existing questions.
Am I still sharing or no longer?
No. So
okay, good.
Good. So we have a few questions.
Yeah.
None of them are very relevant, I think, but we can try to get them. So please, for the audience, put your questions and upvote your favorite questions. So the first one is very simple. Is there any parameter that define the perfectness of a quantum circuit?
The perfectness. Well, I don't know what the word perfectness is quite, but so if you have to run a quantum circuit, you break it down in some elementary gates that your hardware provides. Let's say you're working with IBM devices, and that could be just single qubit gates, rotations around the x-axis or around the y-axis, or some control z gate. And then if you look at, say, IBM devices in the cloud, you'll get some specs. You get, say, if I do a Control-Z gate, I will have an error probability of 0.1% or something, right? And that is an estimate of how well you do that gate. And so typically, researchers try to assess for every elementary gate they do, so single qubit and 2-qubit gate and measurement, they try to assess this error rate, which is a measure of the perfection, how good this gate is. I hope that answers your question.
Yeah, I just want to remind the audience. Yes, 2 days ago we have a benchmarking lecture, which is more or less talking about that, measuring the different errors, and also the Korean's time. So all these metrics will actually kind of like measuring how perfect is the quantum circuit. Usually it's more like what Professor Terha was saying. It's the error rate, so the reverse. You can do 1 minus that, it would be like fidelity. That's like more like perfectness. Okay.
Yeah, the thing is that it's not unique, but yeah, there's indeed. If there's enough separate session out, it's good. Yeah.
Okay, moving on to the next one. Not sure I understand completely. Can you share some key consideration or potential point of failure for QEC in hybrid pipelines?
Okay. Yeah, I'm not sure what I mean. I understand what you mean by hybrid. So hybrid, I understand that you have different types of qubits, or quantum information carriers, and you convert one to the other, or you use one for something. So, for example, for trapped ion qubits or neutral atom qubits, you believe, and even also for superconducting qubits, you would like to switch those qubits to optical qubits. Right? Why optical? Because then you can use optical fibers. Besides losses, they're quite well protected. But the problem is that the conversion, which is called transduction in superconducting platforms, is often a very noisy component. It's a component where, you have to... The point is that the frequency of optical qubits is very different from those of microwaves. So in microwaves, it's, in the microwave, very low frequencies, so low energy. Optical qubits have very high energy. So you have to supply power, but this power may also induce losses. So this is not, I think it's also something that IBM has, for example, looked at. But the point is, it is important. These are components that we'll need. Maybe not to optical, but we need to. It is very interesting to convert one type of qubit to another type of qubit. Because that creates a lot of versatility, of course, right? Because one qubit has an advantage because you can, it can travel a long distance, right? Another qubit is stationary. So.
Mm-hmm. Yeah, that's a very interesting idea. Maybe I ask a follow-up questions. What do you see from different kind of like qubits? What do you see? Which ones are more suitable for a certain application? Like some are for computation, some for memory, or some for, or is there a clear view?
Yeah, that is, of course, any qubit which has a long T1 and T2 is good for memory. And you see, for example, for spin qubits, these times can be, and nuclear spins also can be very long, whereas the gate operations are much harder to get, like very low error rate, like the relative, error rate you get from storage. So what that enables is a little bit more leeway. So, and it's not the case for superconducting qubits. The T1s are increasing; they're getting longer, and 2-qubit gates are still challenging to really push the numbers down, I would say, although achievements are made. But for the platforms like the spin qubits, or nuclear spins and V centers, it offers, like, if the error rate while the qubit's in storage that you don't compute on it is very low, it gives you a bit of time to, entangle some other qubits to create a link through which you want to teleport quantum information. So it gives you some, additional time to link structure. So several platforms use, say, okay, NV centers. I have one NV centers with some nuclear spin. I store information. I have another NV center with nuclear spin, store some information. I want to create an optical link, but this has a low rate of occurring. Optical link, I really want to create sort of an EPR pair. but this has a low success rate. And then having, a long coherence time is quite important. But yeah, so it's nice, of course, if you don't touch your qubit, that they don't fall apart, right? That's always advantageous. You can always say that.
Yeah. So actually, it's quite interesting because like classical computer, there's also different kind of like processors or different kind of like storage, like MRAM, or like for medical a magnetic part to store, or maybe faster memory, like different things. Or maybe in future
Yeah,
the quantum
true.
will be different kind of.
Well, I can exactly, but maybe one comment about that, because you can think about indeed different hardware for different parts of the computer. That is possible, but you can also think about different codes. So, for example, IBM works on these LDPC codes, which are good in terms of overhead because they encode many more qubits per physical qubit, so to say. But you can think also about them as storage codes. So the idea is you have many logical qubits in storage, and that storage is quite dense, but it's not the ideal platform for computing. So when you want to compute, you pull a subset of qubits out of your storage, and then you compute with those, right? But this is all open, how that's going to develop, I would say.
Okay, that was a great question. Okay, moving to the next one. It's quite general. What are some more interesting recent development in quantum error corrections?
Okay, well, I think one is the quantum LDPC code sort of explosion. We've been kind of a little bit stuck. The surface code's been the sort of favorite code because it's so easy, it has a high threshold, and because the experimental efforts were kind of behind, that maybe we didn't dare to think enough about other codes. And there's a lot of sort of developments of different codes that may be more demanding experimentally, but then it also depends on your platform. Now, one thing I want to mention that I find personally interesting, so generally quantum LDPC codes, I think, is an interesting development. But one thing that I like is, so for something like the surface code, it seems that every qubit has to talk to 4 other qubits, meaning it has to do a CNOT gate with 4 neighbors. And for a long time was believed that that's the only way to do this. And if you have to talk with 4 other qubits, you need 4 couplers. Let's say you do superconducting qubits. If you want to talk to another qubit, you need a CNOT gate or a Control-Z gate with that qubit, and that requires a coupler. So that requires a little bit of hardware on the chip. And so there was a paper that reduced that from 4 to 3. So basically showing that the surface code, you can run the surface code without any loss in performance and only have every qubit talk to 3. And we generalized it this for a wide family of code. And I still think there's room for optimization and creativity there. And so what is interesting is that there are developments in quantum error correction that say, hey, my hardware is this, it's hard to connect up a lot of qubits, let me come up with some creative idea, which in the end is highly mathematical, that allows me to have this construction. So those, I think, are interesting developments. I hope that answers the question.
And what do you think, what causes the explosion of QLDPC code for the last few years? Is it like just a coincidence, someone look at it more in detail and then inspire others, or there's some other background development?
I think it's a mix. It's a mix of things. So first of all, okay, so you have to understand what's a good LDPC code. And so a code is usually, it's the number of physical qubits, and it's the number of logical qubits, it's K, and it's the distance. So there are 3 parameters that characterize a code. And a good LDPC code is one which is these local checks, and then K over N is a constant, meaning that if I want to encode, 10 logical qubits, maybe I need 100 physical qubits, so that's a rate of 1 in 10. And, if I encode, 200 logical qubits, I'll need 200. 20 logical qubits, I need 200. So the rate stays constant. I can grow this. So the rate has to be, so there were codes for which this rate was constant and were local check. But then you also want the distance of the code. That can also grow as a function of the number of physical qubits. Maybe you want the distance also to scale with the number of physical qubits. And that was believed you could first, for a long time was believed maybe there was a barrier that you could only get it to up to the square root of the number of physical qubits. Like if you have the Tor code, which has, it's a sort of a d by d lattice, so that's d squared is n, but the distance is actually the square root of, is d. Okay, so the point is there was believed to be a barrier, and that was improved. Somebody crossed this barrier, so there's a paper by Hastings and Ha and O'Donnell that said, hey, here are some codes that go over this barrier that we may believe there exist. And then there were people that improved this. So actually my ex-PhD student wrote a beautiful paper with an improved constructor and a conjecture, and then it was proved that good LDPC codes actually exist, and here are the constructions. Sorry, my answer is a bit long. So that was one development. That's purely because these codes have not shown their practical benefit. And on the other hand, there were like the groups like IBM with the gross code and the bivariate bias. These were explicit codes which were not good LDPC codes, but really outperformed the surface code in a pretty dramatic way. Right? So that's by using non-local connections, by going beyond this sort of 2D planar stuff. And then, and this family of bivariate bicycle codes is actually a subfamily of 2-block group algebra codes. You can read all about error correction codes on the Zoo, by the way. There is a nice website, the Quantum Error Correction Zoo, where you can see all codes discussed and references. So these codes fit in a general framework. So then people start to say, hey, can I vary them? Can, these IBM codes, can I make them different? Or can I put boundaries on? Or and then now the new question is, how can I do universal logic in a very efficient way, also in codes that encode many logical qubits? Sorry, my answer is a bit long, but I hope this was...
That's very good. Thank you very much for the answer. I think we can take 2 more questions and we can wrap up the session. The next one is about what's the approach to error correction specifically used as this Gaussman, Kitaev, Pritzker code for bosonic modes?
Yeah, I'm sorry, I didn't cover that, and it is a very interesting development. So in some platforms you have qubits available, but in many platforms you also have oscillators. And maybe you know about the harmonic oscillator from physics studies. So you have, for example, for your superconducting device, you have resonators. They have a resonant frequency, and you can use such a resonator, and at the particular resonant frequency, you can also use it to encode a qubit. And in this resonator, you can put a state with 0 photons, 1 photon, 3 photon, or something like that. So it's actually a very large space. And there are specific codes that say, well, if you're in that resonator space, which is very large, maybe I can take a specific subspace that is very handy and allows me to correct errors. And the Gottesman Kitaev-Preskill code is an example of such, picking such a space and a code that could, is implemented for a superconducting resonator, for example. And there have been, and this is also still in the running as a different interesting platform because it uses that type of hardware quite nicely. It could also work in the optical regime. That's for just optical qubits.
Okay. I think the next one is the last one, and it's a fundamental question. How is entropy defined in a quantum information theory?
Okay, so there is a basic quantity that's von Neumann entropy. If I have a density matrix, which is the generalization of a probability distribution, I can take its entropy, right? If I have a probability distribution over bits, the entropy, the Shannon entropy can be, it's between 0 and 1. And I can do a probability density matrix of a single qubit, and then the von Neumann entropy, again, is a function between 0 and 1. So that is a basic. So the thing is, if I have a pure quantum state, that von Neumann entropy is 0. I know the state. And if I have a state that's noisy, that's a density matrix, not pure, then that entropy is non-zero.
Okay. So I end this with my own questions, and we like to ask this question about careers because many of the people are new to this field. And so for you, I want to ask if someone want to join this field to do like maybe quantum error correction research, do you have any tips or any suggestion for them if they want to approach this career?
Um, yeah, well, I think what's nice is people can come with a lot of different skills, math, computer science, good programming, engineering skills. So, but you should find, your own strengths, right? What do you bring to the field? And that, I think, is important, that go with a team in which you can use these strengths, because quantum error correction is, or quantum computing is very broad. Like, we need people from everywhere, but there's also a bit of competition, of course, to get in to the spots that you want. So use your strength, right? And say, hey, here is where I can contribute, and maybe not there, and then I need to look for the applications or the people that specifically match with my skills. Yeah.
Okay. Maybe just to follow up and thought about it. When you say that you went to this conference and you saw a lot of people working on error correction, and then you choose to stay away, and how do you ended up back to this field?
Yeah. Well, how do I ended up still doing error correction?
Yeah.
Yeah, actually, this was, I think, so this came actually through John Preskill. So I was
Okay.
1
Interesting.
year at Caltech, and there was this fault tolerance, because my first paper on fault tolerance was about a more general noise model under which you could prove the fault tolerance threshold theorem. And I remember reading lecture notes of Preskill, or they were published in some book, as a basis for this, to understand the basic requirements and assumptions of the threshold theorem. And actually, I have a funny anecdote, because I was reading in that book, and I was highly pregnant with my first baby, and I was reading that, and I threw up over the book, because when I was going into labor. So I was reading the book while I was about to give birth. So that's a
Very
funny anecdote.
interesting.
And
And
with
Presley also gave a lecture last week. So it's really amazing to see these pioneers are all connected. I think at the time the
Yeah,
field
yeah.
was
Right. Yeah, I think that's also very nice, that it's been a very good community, and we stimulate each other. Yeah. We had a sad, maybe you've heard this also, Ray LaFlamme died a few weeks ago, who's one of the pioneers in this area,
Mm,
quantum error correction. He's done amazing work
yeah.
with CNIL in the past, as you saw, that I referred to, and also later on. Yeah.
Mhm.
Okay.
Okay. Yeah. So with that, I think we thank everyone for joining today, and I think thank you, Professor Teo, for giving us an amazing overview of the historical development of quantum error correction. And join us for our next two lectures by John Watchers on the basics of quantum error corrections. All right.
Okay. Thank you. Okay. Bye bye.